Okay, now this time I just want to discuss polar and non-polar because that's difficult and it causes lots of problems. So I'm going to look at 3 compounds. 2 of them you've already done on your sheet, but we're just going to go over them again and take everything into consideration. So for a start, I'm going to look at arsenic hydride. Now that was one that was on the worksheet that you did. Let's look at everything we know about arsenic hydride. So arsenic is in group 5. That means there are 5 electrons on its outer energy level available for bonding. So 5 electrons. Hydrogen, remember its valency is 1. There are 3 hydrogens, so that means that's going to provide 3 electrons. We'll look for 3 electrons during bonding. So altogether we have these 8 electrons in arsenic hydride, which infers 4 pairs. Right, so I've got 4 pairs of electrons. I can see from the formula AsH3 that there's only 3 bonding pairs. So of these 4 pairs, 3 are bonding pairs. 1 therefore is a lone pair. Right, how are they going to arrange themselves? So arsenic is the central atom. The 3 hydrides will place themselves around that arsenic, and they'll be pushed by the lone pair of electrons which reside on the central atom. All of these will push each other away. The bond pairs will repel the bond pairs, the lone pair will repel the bond pairs. So according to electron pair repulsion theory, all of this repulsion happens, and you come up with we'll say if it was a tetrahedral molecule, it would have a bond angle of 109 degrees, but this lone pair reduces that bond angle by about 2.5. So, your bond angle is around 107 degrees, somewhere around there. That's the first thing. Now, let's look at the electronegativity difference. Okay, so arsenic has an electronegativity value of 2. And these hydrogens down here, which are bonded to it, these hydrogens have a difference or their electronegativity is 2.1. So therefore, your difference is going to be 0.1. Now that is really very small. It's practically pure covalent bonding within the molecule. So it's practically pure covalent. It's much closer to pure covalent than polar covalent, which means that the forces of attraction between these arsenic hydride molecules are mostly van der Waals forces. So you've got van der Waals forces of attraction. No dipoles then, absolutely no dipoles. No dipoles, there is no separation of charge, so van der Waals forces. And if that's the case, if it's van der Waals forces, then it has to be a non-polar substance. Okay, non-polar substance. If there are only van der Waals forces present, has to be non-polar. That's the first one I wanted to have a look at. Now let's have a look at another one on the sheet, which was hydrogen sulfide. Okay, now hydrogen sulfide, what's the story with hydrogen sulfide? Sulfur is in group 6, there's 6 electrons on its outer energy level. Hydrogen has a valency of 1, we have 2 of them, so that's 2 electrons, which gives us 8 electrons, which means 4 pairs. Now I can see from the formula H2S that there is not 4 bond pairs. There's only 2 bond pairs. Now, is it that there's 2 single covalent bonds or 2 single bonds, or is it that there are 2 double bonds? So you have to take that into consideration as well. Now, double bonds. I'm going to mention something about double bonds. Double covalent bonds, for us, will only involve carbon. So keep that in mind. Double covalent bonds, only carbon. So that means this compound here has a central sulfur atom and it has 2 hydrogens, which are going to be pushed closer together by 2 lone pairs. So these 4 pairs of electrons now, I know there's 2 bond pairs, I can see from the formula, 2 bond pairs, so the other two pairs have to be 2 lone pairs. And remember that a lone pair reduces a tetrahedral bond angle by 2.5 degrees. So you've got this tetrahedral bond angle of 109 reduced now by about 5 degrees. So you're down to 104 degrees of a bond angle between those. So that's the first thing. The next thing is, let's continue now and see, is this substance polar or non-polar? Look at the electronegativity difference. So sulfur has an electronegativity value of, what's sulfur? It's on my table here now. Sulfur has an electronegativity value of 2.5, okay, and hydrogen is 2.1. So that means your electronegativity difference is 0.4. Again, very, very weakly polar covalent, if at all. So it's very, very weakly. A very weakly polar covalent bond. Again, what type of forces now of attraction are going to be between the molecules? The dipoles that exist, because the difference is so small, is going to be non-effective. So the very weak dipoles, very, very weak dipoles, because your electronegativity difference is so small, which means you've got mostly van der Waals forces between the molecules. So if you have mostly van der Waals forces between the molecules, even if the molecule is non-symmetrical, which this obviously is, it's non-symmetrical, then that substance is going to be a non-polar substance. Now, a couple of things I'm mentioning here now. This hydrogen sulfide and this arsenic hydride, they are both non-symmetrical, as you can see. They're both non-symmetrical. So you could say, okay, non-symmetrical molecule then, and if there are dipoles present, then it's going to be a polar substance. It's not the case. If it's very, very weakly polar covalent or nearly pure covalent, then the van der Waals forces will affect whether it will be non-symmetrical or symmetrical. A substance will only be polar if it has dipole-dipole forces of attraction between the molecules. So non-symmetrical, van der Waals forces of attraction between the molecules would suggest non-polar. Now there's one more we're going to have a look at just to prove all of that, and that's called boron trichloride, BCl3. Boron is in group 3, so it's got 3 electrons available for bonding. So that should be BCl3. Chlorine, of course, has a valency of 1, and there are 3 electrons, so that's 6 electrons altogether, which means 3 pairs. Okay, and I can see I've got 3 bond pairs from the formula BCl3. Okay, so 3 bond pairs. So boron is going to be the central atom, and it's going to be surrounded by 3 chlorines. And of course there's no lone pairs, so they'll all equally be spaced between each bond pair will be pushed with the same repulsion. So our bond angle here then is 120 degrees. Okay, so that's my boron trichloride. Now, let's have a look at the electronegativity difference. Boron's electronegativity, if I look at my electronegativity table, is 2. Okay, so boron has an electronegativity of 2. Chlorine is stronger. It has an electronegativity of 3. Okay, so that means the electronegativity difference is 1. So a difference of 1, which means polar covalent bonding, without a doubt. Polar covalent bonding. There is no doubt here. Polar covalent bonding. And there is no, it's not weak, it's absolutely, without a doubt, polar covalent bonding. Okay, that means that there are dipoles present. So we've got obvious dipoles. Dipoles are present. If there are dipoles present, that means that I have to now look at whether it's symmetrical or non-symmetrical. So I can see here that this has 3 lines of symmetry. So no matter which way I place cut my molecule, it's going to be symmetrical. So it's a symmetrical molecule. Now there are dipoles present, but it's symmetrical. Now I also want you to do this. If you're ever asked whether a substance is polar or non-polar and asked to give a reason, it is a symmetrical molecule. What does that mean? This means that the centres of positive and negative charge coincide. So the centres of positive and negative charge coincide. So let's just have a quick look at what that means. Boron, 3 chlorines around them like this. This boron, remember the chlorine is more electronegative, so these will be the negative sides. The boron will be the positive end. So the centres of positive and negative charge coincide. So this is a centre of negative, 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 and they all sort of coincide around that boron molecule. So that's what that means. So because of that, we're going to say that this compound, it is a non-polar substance. Even though dipoles are present, it's non-polar. Okay, so what I wanted to bring your attention to was these 3 compounds. Each one of them is non-polar. These 2, this one you could say all very weakly polar covalent, this one practically pure covalent, and this one is absolutely polar covalent. So we look at the internal bonding and then we can deduce from there when we move on whether it's going to be polar or not.